February-March 2021, Paper 2, Variant 2. Question 1A, Part 1. Draw a curve on the axis to show the Boltzmann distribution of the particles of the gaseous Krypton atom. Okay, so you need to label the axis. So the y-axis is the numbers of particles or molecules. In this case, is atoms, because it's a Krypton. And kinetic energy for the x-axis. And you have to draw for the normal Boltzmann distribution this curved, and this one you just need to label T1. Label curve T1. Okay, so this is the Boltzmann distribution for this part. Later the dotted line in the part 2. Okay, on the diagram, same diagram, A part 1, draw a second curve to show distribution of energy of the Krypton at higher temperature. Higher temperature means all the particles now, they will absorb the energy and all the particle will move faster. Means the whole distribution, it must shift right. Why shift right? Because to right means kinetic energy increases. So that's why when temperature increases, kinetic energy increases. So it must move to right. Because the numbers of particles is still the same, so it cannot just the whole curve move to right without any change. So it must move to right, and it must be a bit lower. So move to right and a bit lower. So you need to show this part, the part that has more kinetic energy. And you have to label these lines as T2. Okay, B. The Boltzmann distribution assumes that the particles behave as an ideal gas. State two assumptions of the kinetic theory for this ideal gas. The two most significant assumptions, they are the IMF and the volume. Okay, no van der Waals forces or IMF between the particles. Means there will be no attractions or repulsions between particles. Okay, and this is one of the ideal gas theory. Another very significant assumption is we assume the volume of the particles is negligible compared to the volume of the container. Volume of container, let's say, is this, and the particle is just very tiny spot inside there. So the volume of the gas particles is negligible. You can put another assumption, which is the collision, and the collision between particles and the particles with the wall, they are elastics. Okay, for part 2, 2 grams of Krypton gas is placed in the sealed container, and this container has 5 dm³ and 120 degrees C. Calculate the pressure in Pascal of the Krypton in the container. So this one you have to use the combined gas law, PV equal to nRT. Make sure you use all the standard unit in this combined gas law. Pressure must be Pascal. Volume must be meter cube. Okay, Pascal. Volume must be meter cube. N is just a mole, R is a gas constant, T must be in Kelvin. Okay, so you need to do some conversion. Okay, because this question you need to get the pressure, so you just move the V to the other side. Okay, so N is given, the gram, you convert to the mole, 2 gram over the molar mass, you get the mole, 0.02387, times the gas constant, times the temperature, so it's 120 plus 273. So we convert the degree C to Kelvin. And the last one is the volume. Volume is dm cube. From dm cube, if you want to convert to meter cube, so must divide by 1000. Must divide by 1000. So you get this 5 times 10 power negative 3. Okay, then you calculate, you get this 15591. If you want to put it in the 3SF, then this is the 3SF, 15600 Pascal. Part 3. State and explain the condition which krypton behave most likely like an ideal gas. So 2 very important conditions, which is the low pressure and high temperature. So we know that low pressure volume is higher, is larger. So therefore, the volume of the particles, it can be further negligible. Means is more insignificant. High temperature, all the particles move really fast, more kinetic energy. So the elastic is collision is greater. Means the collision is more elastic, and so with these 2 conditions, right, the volume of the particles, okay, and the van der Waals forces between the particles, they are now insignificant. So just remember 2 special conditions, low pressure and high temperature, which the volume of particles and the van der Waals force between the particles is more insignificant. Okay, part C. Krypton reacts with fluorine. Okay, from this krypton fluoride. The activation energy given is 385 kilojoule per mole. Enthalpy change is 60.2 kilojoule per mole. Use these 2 in 4 to complete the reaction profile for the formation of this krypton fluoride. So for this one, very easy. You just need to draw the correct energies diagram, because it's given the formation of the compound is the endo. So means the product you have to put at higher energies level compared to reactant. Then you put the delta HF, okay, equal to 60.2 here. So this one is the delta HF, the formation from the reactants, which is the elements, okay, to form these products. Okay, and of course you have to put the EA. EA is of course much higher than the delta HF. So this is the EA, right? So this one, this part, the energy needed, okay, to overcome to form the products, which is 385 kilojoule per mole. Okay, part 2. Explain in terms of activation energy and the collisions of particles, how an increase in temperatures affect the rate. We know that when the temperatures is higher, the rate is higher. It's always true. because all the particles, they have the higher kinetic energy, like what I said just now. This one is lower temperature and the dotted line is higher temperature. If now the EA is this, so this is the standard EA. With higher temperature, it has more molecules equal or more than EA. So that's why the successful collision is more. So what you need to mention is just more particles that have energy same or more than the EA at higher temperature. Therefore, frequencies of the successful collision is increases. Okay, that's all for this question. Thank you.